Hello and welcome to today's IWCS webinar. My name is Connie and I'll be in the background answering any WebEx technical questions, and I'll be your Cisco producer for today's event. Now I'm pleased to turn the webinar over to Ed Fitton, your IWCS moderator. Ed, you now have the floor.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly, and they will respond individually to you. Today, we are pleased to welcome Tanya Artingstall, Senior Technologist, Mexichem Specialty Compounds from Melton, Mowbray, UK, who will be presenting her paper on halogen-free compound solutions to address thermal stress cracking in extreme conditions. Tanya Artingstall started her career in the plastics industry at Lindsay & Williams, Scapa Polymerics, which via acquisitions became Alphagary Limited and now Mexichem Specialty Compounds. She gained her BSc honors degree in polymer science at Manchester University in 1998. She went on to achieve an MPhil degree, participating in a research program into the behavior of fire retardants in cable materials. Tanya has 27 years of experience in the development of technical support of products for the wire and cable industry and is instrumental in the development of next-generation compounds in Mexichem's Megalon LSHF compounds portfolio. Tanya heads the Mexichem UK development team specializing in development and design of low-smoke halogen-free compounds. Tanya, we welcome you to present at today's IWCS webinar series.
Thank you, Ed, for the kind introduction. Good morning, afternoon, and evening to all of you, my listeners. Thank you so much for kindly joining me on this webinar. My presentation, titled Halogen-Free Compound Solutions to Address Thermal Stress Cracking in Extreme Conditions, discusses the factor that could influence the performance of halogen-free compound materials in extreme environments. So, I'm trying to move on my presentation. Presentation will go over the following topics: material selection, characteristics of low smoke halogen-free compounds, the troubleshooting of a cracked cable, the DSC analysis techniques trusted by Mexichem, and I'd like to go through an example of cracked cable review that we've done. Then we will conclude the presentation and the webinar will be open to any questions that you, my listeners, may have. So let's get started. Material selection. As all cable manufacturers are well aware, there are many global technical requirements, test standards, that the cable that they're trying to make will have to conform to. These include British standards, Norwegian NEK standards, US Underwriters Laboratories, and London Underground, LVULs, to name a few. There are usually similarities between these standards, and in some cases, harmonisation of standards, such as the European norms, EN specifications, are in place. So am I just trying to get things to move on. For the cable manufacturer, there is a whole host of materials that could be selected for the cable compound application, such as PVC, elastomers, engineering polymers, and the subject of today's presentation, halogen-free compounds and others. With some of these materials, such as low smoke halogen-free compounds, they are unique in the way they behave, and traditional or available equipment and processes may not be enough or even capable to fully realise the potential of that selected material's properties. Thus, to understand the nature of the chosen material is very fundamental to fully optimise its properties. MSc Mexichem believes it's very fundamental to work with partners and suppliers who can assist with points of failure. After the title of this presentation, I would like to focus on low smoke halogen-free compounds. Now, we know that these materials do meet a whole host of global biotest requirements and other test criteria. They can be developed to match the performance of other materials such as PVC in terms of, say, processability and flexibility. They are, depending on the end use of the environment that the low smoke halogen-free cables are chosen for, it could, you have to choose a high performing compound to meet certain applications where they're going to be installed in arid or humid spaces. For such environments, these formulations must be robust enough to meet the requirements. One particular concern or requirement will be to address any thermal stress cracking concerns. So choosing a compound with improved thermal stress crack resistance performance is very important. And of course, all these cables, such as halogen-free compounds, will have to be tested to ensure survival in these demanding environments. So for cables to be installed in extreme harsh environments where cracking could be a problem, the choice of the material, the compound formulation, is very important. That is, the material chosen must have property performance to satisfactorily withstand the extreme conditions that they need to perform in. Having chosen the best suited grade, a high performing grade, the manner in which these materials are processed is of key importance to be able to achieve the optimum performance of that cable in the field. So it's the right material to meet all the criteria of the end application, but the process method has to be optimized to the characteristics of that compound. So let's just discuss this point further. Low smoke halogen-free compounds are generally highly filled with metal hydrates, flame retardants, so your aluminium trioxides and your magnesium hydroxides and calcium carbonates maybe. In the main, these low smoke halogen-free compounds will contain or be based on semi-crystalline polymer systems. Thus, halogen-free compounds will not behave like amorphous materials. This is a significant point in that they will have much smaller processing window when you compare them with PVC. So, let's recap what is needed for a material for a cable that is going to be used in the harsh environment. Well, cables installed in this environment will more than likely be designed to consist of steel wire armouring or steel wire tape wrap. These cables will be installed in temperatures happening in harsh and hot environments with temperatures reaching 40 to 50 degrees C. And often they will require the conformance to many British standards regulations, which often have to meet hot pressure test at 90 degrees C. So we're talking i.e. Cable specifications such as LTS1 and LTS4 types as described in BS 7655. So to ensure material chosen is able to withstand the harsh environment described, such tests as this one shown here, employed by Mexichem, is the use of thermal stress crack resistance. This test uses the same equipment and preparation method for the environmental stress cracking, with the exception that instead of placing the prepared samples in detergent in Igipal, they are placed in ovens at different temperatures and the specimen observed over a period of 14 days to determine the temperature where no cracks occurs. The picture shows some cracking at 60 and 70, and you see at 50 there are no cracks. So this particular test was a 50-degree level for stress cracking. So moving on to processing techniques. As we mentioned, the halogen-free compounds will be semi-crystalline in nature. They can develop, because they are semi-crystalline in nature, they can develop frozen in stress if cooled too quickly or too rapidly in the cable making process. What is happening is that the sheath of jacketing is drawn out to cover the core, and it is prevented from shrinking back and thus not attaining equilibrium. That is, the polymer are not allowed to obtain the crystallinity it wants to achieve. The stress level in the jacketing sheathing will then be greater than the strength of the polymers, which leads to cracking. In other words, equilibrium is prevented by the lack of chain mobility at temperatures below its melting point. You might ask, how can this be determined? How do we know that frozen in stress is occurring? Well, we believe that frozen in stress can reveal itself as false melting points, peaks and points using a DSC analysis. DSC analysis, so if we know this, is a differential scanning calorimetry thermal analysis technique. We have found via a process of heating the cable material beyond the melting points of the polymer, then following that, cooling it at a very slow rate to ensure equilibrium, and then doing a reheat. The graphical representation of the cycles will reveal differences between initial and subsequent heat cycles. These differences indicate of changes or optimization needs to be made to the processing technique. The low smoke halogen-free compound, we believe by achieving equilibrium during the processing, would lead to cracking in the field being avoided. I would now like to go through an example where this analysis has helped us to work with our customers or cable manufacturers to obtain good performance in the field. Our analysis was done on 3 cable samples. Cable 1 is a good cable with a small diameter and thin wall. This cable has been consistently good in the field and no failure points have been raised over 4 years of using this cable's size. Cable 2 is a good cable again, but this time it's a larger diameter with a thicker wall. No cracking issues have been reported with this one. Cable 3 is the same cable design as cable 2, but in this case there was a failure point raised with this cable. Here at the bottom of this slide, I have shared with you the test method that we use for our DSC analysis. We heat a piece of the jacket from room temperature to 200 degrees C at a rate of 10 degrees C per minute. We then slowly cool it at a very slow rate from 200 to minus 25, moving at 5 centigrades per minute. Following that, we then reheat. We do the second heat cycle, again at the rate of 10 degrees C per minute, from minus 25 to 200 degrees C. So, as you can see, this is a very long test. Each test for one piece of cable would be lasting just short of 1.5 hours. This slide it shows the graphical representation of the DSE method on cable 1. The blue dashed line is the first heat cycle, the green line is the cooling cycle, and the red solid line that you see there is the second heat cycle curve. When we reviewed this, we can see that the blue line overlays onto the red solid line. This indicated that the halogen-free compound was processed well and did not contain significant frozen in stress levels. This outcome is most expected as this was a good cable. Obviously, the smaller diameter and thinner wall made it easier to cool slowly, which allowed the material to reach equilibrium and was then free of significant stress levels. On this next graph, we again have the DSE heat-cool cycle for the larger diameter cable, which had not encountered any issues in the field. Here we see similar behaviour to cable 1. The dotted blue line is overlapping the red second heat cycle curve. Again, this would indicate this is a cable that had been processed well and did not contain significant amounts of frozen in stress in the main. Although the cable was identified as good with no crack issues, you can see between 35 to 70 degrees C there, that where there's some small disparity between the curves. This would suggest that small opportunities to optimise processing could have been done. A thicker jacket wall is obviously more difficult to cool slowly and uniformly. Now we turn to the last cable under review. This is a cable that had some cracking issues in the field. This time, when we look at the dotted blue line and the red line, large differences are revealed. The true melting behaviour of the jacketing halogen-free compound is revealed in the first heat cycle. This heat cycle appears to have multiple false melting points, which are significantly large or different from the subsequent heat cycle after cooling and equilibrium had been optimized. This is a good indication that frozen in stress is present. Now, some of my listeners are maybe good analytical bods, very experienced in analysis via DSC, and having in-depth experience of them. You might be wondering if the false melting points self-produced by the slow heat cycle rate. I would generally be in agreement with this hypothesis, except that, as I said earlier, halogen-free compounds are highly filled, and I believe that the DSC heat cycle would not give the polymer enough mobility to create these false melting peaks. In less filled systems or pure polymers, there would be an adequate time and space for mobility of the chains to create these false peaks. So, based on the DSC analysis that Mexichem, on this DSC analysis, Mexichem concluded that the failed compound cable had cracked in the field, had indeed exhibited or contained frozen-in stresses. Once discovered, a technical support trial was undertaken, and during this, recommendations were made to cool the cable as slow as possible during production to minimize frozen-in stress. To achieve this, an additional water trough was added to the line that allowed the extruded cable to run through heated water to cooler water, and this achieving gradual cooling of the hot extruded cable. Once done, this optimally processed cable was evaluated for the very same ESC heat cycle. And as can be seen on this slide, the frozen-in stress, frozen-in stress or false melting points did not show up. No false melting points, and the curves are back to overlapping one another. So, in conclusion, low smoke halogen-free materials are appropriate for a variety of cable applications. More and more developments are coming along to further meet demands of cables installed in harsh environments and the requirements that comes with them. Once a cable is identified to meet all the physical attributes required by the cable standard, then an understanding of a particular and peculiar processing behaviour is needed to be able to optimize processing. As the market of low smoke halogen-free compounds continues to grow in different cable designs and environments, cable manufacturers are faced with improved field performance and optimized processing techniques. Working with suppliers with in-depth knowledge about available polymers and analysis methods, I think this is an invaluable tool to help with fully realizing the material's properties to help with the demands of the widening wire and cable market. So, ladies and gentlemen, that concludes my presentation, and I thank you all for listening.
And thank you, Tanya. And at this time, we will ask as many questions from the attendees as time permits. And I will start with this first question. With halogen-free compounds now being used in many cable designs around the world in a wide variety of environments, are there any other functional parameters beyond just thermal cracking that should be of concern using conventional halogen-free technology?
Sorry, Ed, can you just repeat that again? So I didn't get the question again.
Certainly. With halogen-free compounds now being used in many cable designs around the world in a wider variety of environments, are there other functional parameters beyond just thermal cracking that should be of concern using conventional halogen-free technology?
There isn't any that springs to mind. I'm sure some of my listeners might be saying there is, but I think whether it's disguised as something else, it comes back to the stress cracking. I think it would be whether it's tear or just like the hot pressure or indentation or scratch resistance. I think it all comes back to the same functionality of stress in a cable. I hope that answers the question. If not,
okay, thank you. Thank you, yes. Next question. Have regional standards been modified to adopt test methods and pass-fail criteria to verify performance in harsh environments?
No. From our experience, I think that stress cracking can be subjected to each company's methods So people will be using either full cable or pieces of sections of cable, doing various notches and different bends. Some people will do put out, bend the cable at greater than or less, much tighter, around a tighter radius, and place it in just in a yard. But these obviously are companies that enjoy high weather, but good temperatures all the time, so they're able to put it in their yard and just see the performance of that over time. So there's no standardisation, or I'm not aware of any standard. This is the way to test stress cracking, or test for the possibility of stress cracking of the cable compound.
Okay, thank you. Next question. Which has the greatest impact to prevent stress cracking of halogen-free compounds? Processing, compound formulation, or cable design thickness of the sheath?
It's all going to be a balance of all three. Obviously, the cable design, if we talk about the steel wrap or the steel tape, the steel wire armouring or the steel tape, we've got to think about the overlap. How much stress is that overlap? If it's only a small overlap on a steel wrap, that can cause a strain or stress on the cable. The processing-wise, if you were to stress out or draw down the material, the compound material onto the core, onto the cable, then you're producing stress that way. And then, of course, the compound formulation, they're going to have to be optimized to be able to give the best performance for that temperature range. So it is going to be a balance of all three. And the difference in diameter between one cable design to another, that will influence it as well. So all a balancing act, I'm afraid.
Thank you. Okay, next question. Does either temperature cycling or continuous exposure to high heat extreme conditions impact stress cracking more?
I think that temperature cycling impacts it more, because depending on how the cable is installed, if it's freely lying on the desert floor, shall I say, or if it's actually clamped down, then I think the temperature cycling will cause relaxation and contraction and so on of the cable material. So I think that would lead to cracking more readily than if you just had the cable at high temperature. I think that's
okay.
I think that's true of my experience.
Okay, thank you. Next question. Do halogen-free compounds using magnesium hydroxide or ATH have a particular impact on long-term aging or performance in harsh environments?
Let me think. Say that again. That's saying, does the ATH or
sure.
Which of those two materials are more susceptible for use in these environments? There isn't a correlation between those fillers, shall we say, metal hydrates, with stress cracking. What will be a correlation is the types, as in how precipitated they are, how good they are, surface area. So there will be which one you use could be related to stress cracking in the field or damages in the field. But there's no one is better than the other between those two materials.
Okay, Thank you.
Okay.
Next question. How do you obtain a DSC sample without introducing stresses that could affect DSC?
Sorry, Ed, can you just repeat that so I understand the question?
Absolutely. How do you obtain a DSC sample without introducing stresses that could affect DSC?
I'm not sure what the question is asking. How do I obtain a DSC sample that could affect? How do I affect it? If I'm thinking what the question is asking, how do we do it in the lab to affect this, to show the differences? I guess we can work with any tape extrusion or milling. I think it's where you quench something that's been orientated and allow another one to cool down in its own time in the room temperature and test the quenched sample and the allowed to cool down material. You may be able to see that in the DSC performance. Hopefully that answers that question. But if it's not quite right, I can elaborate more.
Okay, thank you. Next question is, we have seen a number of cases in the UK of cracking of LSHF multi-core flexible cables used in modular lighting. Some of these are associated with intense light exposure, such as heat effect and no UV. Often these cables are non-standard. Any comments?
Non-standard. I'm trying to understand the question. So we've had cables that are placed in the lighting and they have issues. Not without understanding more of the question, I can't answer that from here. So I'm pleased to answer that outside this forum if I can. But I'm not quite understanding that.
Yep, very, very good. Very good.
Okay. Mm-hmm.
Next question is, this would poor metal hydride dispersion and or grafting in compounding also lead to stress cracking?
Yes, I believe so. I think as a lot of things, good homogeneous mixing, dispersion of the compound formulation is also key to getting good performance in the field. So yes, making it right, making it good and homogeneous to allow the cable manufacturer to extrude optimally on his machines will lead to a good cable in the field. So I think the answer is yes to that.
Okay, thank you. All right, next question. If there is no proper screw drive on an extruder for LSHF, i.e. the transport screw, what cares must be taken to avoid stress?
If there's no proper,
If there is no proper screw drive on an extruder for low smoke halogen free, what cares must be taken to avoid stress?
Okay. Again, I'm not 100% on the question, but if we talk about stresses on cable extrusion, what I would be looking for is the tooling design, the actual die and core or tip that is used, whether these are giving a acceptable drawdown ratio for the cable being made and the material being made. So those could also create the stresses. So if you were to use a larger die, then that would give a higher drawdown ratio. You're going to create the stresses in the cable that way as well.
Okay, thank you. Next question. Is there a simple test that can be done at processing to verify that a cable made meets the stress-free environments?
A simple test would be the DSC method. So done at processing, a simple test. The answer would likely be no, because in this study or this review that we did with this cable manufacturer, obviously the cable was tested for all its other parameters and was released with no problems. What couldn't be seen was the stress levels, and only by the DSC method were we able to realise that. So not as I know is the answer.
Okay, thank you. Next question. Have you found a trend between the particle size / surface area and developed inherent stress in the jacketing, such as higher surface materials generate high inherent stress?
Yes, I believe there's a trend in particle size. I think the higher the particles, the surface area, the more likely that you would get the stress cracking. But you can counter that by the use of different polymers. It's, again, a balancing act between the performance you're looking for, with fire retardants, they say, the mechanical properties, thermal properties that you want. So it's the choice of your polymers and your fillers. So yes, there is a trend. I hope that answers that question.
Yes, it does. And I believe. The next question is this: Is it possible to remove frozen-in stress to save a batch of cables?
Is it frozen-in stress? Good question. I would, in theory, would say that if it's possible, you could put the coil of cable into a room or a warm environment, 50, 60, 70 degrees, and allow it to relax. And think that would remove frozen stresses, but unproven, and it's just a thought. I don't know, and I'm not aware of any results to show that. But a very good question.
Okay.
Thank you.
And next question is, what temperature cycling parameters are appropriate in the laboratory?
What temperature cycling parameters are appropriate in the laboratory?
Yes.
Are we talking the DSC, or are we talking about? So we're talking the cable cycling for the stress cracking, or? Well, I think it's not understanding the question too well. I would say it's just whatever your end application is asking for. If you have a cable that are going to be installed where at night they get minus temperatures, and then during the day you're getting hot temperatures. Then if you have capabilities of a thermal cycling unit, obviously you should be testing cables to within that range of your final application.
Okay.
If that's not correct, well, I can come back to that.
Sure.
Okay.
Okay. Thank you very much. At this time, this concludes the Q&A period. I would like to thank you, Tanya, for presenting this very interesting and important topic today. Please note the contact point. Please note the contact points being shown should you wish to contact Tanya after today's event. Each of these IWCS webinar series presentations events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, February 16th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 66 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, October 14th through Wednesday, October 17th, 2018 at the Rhode Island Convention Center in Providence, Rhode Island, USA. In addition, the second annual regional UL and IWCS China 2018 Cable and Connectivity Symposium will take place on Tuesday, March 20th through Thursday, March 22nd, 2018 at the Shanghai International Convention Center in Pudong, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.